Okay, welcome. Lesson 17, scales. Not too difficult a topic, which is nice, right? So we're going to look at model scales. Model scales indicate a change in magnitude between the model and that which it represents, which you know if you're a little kid, right? You get models of little things, models of airplanes, models of dolls, models of all kinds of things, right? Cars, trucks, whatever. Sometimes the units are of both the same quantity, and sometimes they aren't. Like, for example, you can have an architectural drawing, say you've got a 1/4 inch per 1 foot. That is not a unitless scale because inches and feet will not cancel. But down here, model airplanes, it says, are usually on a scale of 1 to 72. That could mean 1 inch or 1 centimeter or 1 mile or 1 meter per 72 centimeters, inches, miles, meters. So this would be a unitless scale. It doesn't show any units, and therefore it's unitless. What this, of course, means is that a model of 1 inch or 1 centimeter will correspond to the reality of the actual object being 72 inches, centimeters, or whatever, the actual length. This 1 to 72 scale is increasingly popular in worldwide die-cast toys and some Japanese characters. In the United States, we usually use a 1 to 48 unitless scale, and it's still more prevalent. But note the scale works the same way as the 1 to 72 scale does. So in the 1 to 48 scale, 1 centimeter of the model corresponds to 48 centimeters of the actual object. Likewise, 1 foot of a model would be 48 feet of the actual object. So here we're going to create a model, a scaled model of the solar system. Okay, so here we're going to create a scale model of the solar system. All right. And we're going to set it so that from the center of the sun, as we make this model, it's going to be 1 yard away. So we need to find the corresponding distance each one of these is away from the center of our model. So if you set Mercury to 1 yard, which it is set to 1 yard, what is the model scale you are using? Well, you're using the model scale 1 yard to 57.9 million. I'm just going to put times 10 to the 6th kilometers. So that's the scale you're using. Now let me just talk a second about the orbital radius. If you have the sun here, I should probably put it in red, right? Hot sun. And you have Mercury, say it is here, small, not drawn to scale. But the orbital radius is the distance from the center of the sun to Mercury. And there's its orbit, and there's its orbital radius. So that's the scale we're using. Is this a unitless ratio? No. No. You can't cancel yards and kilometers. A unitless ratio, like on an architectural drawing, sometimes they have, say, it's 1 inch on the model to 96 inches in the actual building they're making. You can cancel the inches, and that is unitless because units cancel. Units aren't canceling here. It is not unitless. So they want us to use this ratio that we have here, that we were given, to determine how far the other planets would be. Use it to fill in the table. Okay, so we can just say, okay, 1 yard is to 57.9 kilometers, millions of kilometers. As I don't know how many yards, and now I'm doing Venus, is to 108.2 kilometers. I don't have to use the millions of kilometers because they would essentially cancel. Let me show you that. So I filled this in here. This is the distance from the orbital radius to Mercury, and this is the orbital radius to Venus. Now watch. I can cancel this, and the ratio does not change. It'll be 57.9 over 108.2. So I don't need to use this 10 to the 6th when I'm filling in this scale here. Okay, I can get rid of this now and go back to there. So what I'm going to do here is cross multiply, and I'm going to get 57.9 times x equals 1 times 108.2. Divide by 57.9. Divide by 57.9. And I get the distance that Venus will be in this model is going to be 1.87 yards. Let's put that right here, 1.87. A little sloppy, but get the idea. Okay, so we'll do one more this way. So I'm just going to set up our original scale model, 1 yard to 57.9, and I'm going to do this time Earth, which is 149.6. So how many yards would that be? So you can look here and say, well, Venus is about twice the distance from the sun as Mercury. So it looks like 57 or 60 times 3 is about 2.5 times maybe the distance. So that's going to be about 2.5, but we'll see. I'm going to cross multiply. X equals 149.6. Seems repetitive here. I'm dividing again by 57.9. And I'm dividing here again by 57.9. So I am getting 2.58. So that would be put it right here, 2.58. So look at a quicker way of doing this. Notice how each time that I do this, well, to get Mercury to go to 57.9 to 1, you can divide by 57.9. To get this scale the same way, we divide it by 57.9. To scale the Earth, we divide it by 57.9. So guess what we're going to do here? instead of setting up the proportion, I'm just going to take advantage of this fact. So Mars is 227.9, and that's kilometers, or millions of kilometers, times 1 yard over 57.9 millions of kilometers. Now watch this. These cancel, and I almost have a dimensional analysis problem. 227.9 divided by 57.9. And I'll put these numbers up. I'll do one more. The asteroids are 686.1 millions of kilometers times our scale model, which is 1 yard over 57.9 millions of kilometers. Kilometers cancel. 686.1 times 1 is 1, divided by 59.7. So everything is getting divided by 59.7. So I'll just write in the answers. I would do it and check your work. So there's the answer to the distance all the other planets would be if Mercury is 1 yard away. So the aspect ratio is the same. Just a quick note here. So here's Pluto. That's how you can do Pluto. Hopefully you did it, right? This is not the same. Scaling is what we're doing here. Scale. It's not the same as dimensional analysis. So let's say that I want to change 3 feet into inches. Well, I would use a ratio maybe 12 inches to 1 foot. Notice that 12 inches equals 1 foot. So when we're using dimensional analysis, we are not scaling. What we are doing is converting. Whatever you're multiplying by in dimensional analysis, that number is always basically the number 1. Because anything divided by itself is 1. Here, 1 yard certainly does not equal 57.9 million kilometers. So this is a scale. It's different than a conversion, and it's for that reason. So in the book, if you could jump like a frog, a 3-inch frog is said to jump 60 inches. Let's look at that. 3-inch frog is said to jump 60 inches. What is the ratio between the body length and jump distance? So body length is in the numerator, jump distance is in the denominator. So it's 3 inches to 60 inches. And then they want you to scale the first quantity to 1. Hopefully you can see divide by 3, right? Or you can cross multiply and divide. So it's the same ratio, it's just reduced. Is this a unitless ratio? And the answer is yes. It is a 1 to 20 unitless ratio because the inches will cancel. Assuming people can jump like frogs, how far would a 4-foot tall child be able to jump? I'm using 120. When it says unitless, it doesn't matter what the units are. Over here, I have a 4-foot tall person and a child, and they'd be able to jump X feet. That's how you can use a unitless scale. You can cross multiply and divide, or you can recognize that 1 times 4 is 4, so 20 times 4 is 80 feet. So that child should be able to jump 80 feet. Now pause this if you don't understand and go back and make sure you can understand this. Let's say, assuming people can jump like frogs, how far would a 2-meter tall adult be able to jump? Well, that's on the top. So my scale is still the same. It is 1 to 20. It's unitless. So in this case, I'm going to use 2 meters. And for how far the person can jump, I'm going to use X meters. Right? Multiply by 2, or cross multiply and divide, and I get 40 meters. So this is a good idea. It tells you what a unitless scale is, and it runs you through a couple problems showing you how you can use that unitless scale and how it works. So now we're going to assume that we've given that a 3-inch frog, that's the length of the frog, can jump 5 feet. Write this ratio between body length and jump distance. So it's 3 inches to 5 feet. With the first number scaled to 1. So I'm going to scale that first number to 1. So I'm going to divide by 3. I'm going to divide by 3. So the scale, and is it unitless? Is this a unitless ratio? And the answer is no. No. Make the end better. I can't cancel inches and feet. I could convert feet into inches, but that's not what it asked for. Now, assuming people can jump like frogs, determine how far a 4-foot tall child can jump. So I'm using my ratio here, 1 inch to 5/3 of a foot. And I'm going to have inches to feet, inches to feet. So I'm going to have to convert a 4-foot child into inches. So 4 feet times 12 inches over 1 foot is going to give me, the feet will cancel, and I get 48 inches. So down here I can go 48 inches is to X feet. And you can either cross multiply or divide, or I can multiply the top by 48 and multiply the bottom by 48. And if you did that correctly, you would get 80 feet. So you can see it's easier to work with when you have unitless scales a lot of times. Assuming a person can jump like a frog, determine how far a 2-meter person, a 2-meter adult can jump. Well, we have the same ratio as this right here. And that is 1 inch of length or height of a person corresponds to 5/3 of a foot jumping ability, if you could jump like a frog. And this person is 2 meters tall. So I got to convert 2 meters into inches. So 2 meters, I can first convert the feet. Notice 3.28 feet is 1 meter. This is really multiplying by 1. And now I have feet, and I can convert to inches. Again, this is dimensional analysis. And I get 78.72. And so now I'm going to come down here. And I know the length of the person is 78.72 inches. I'm going to find out how far that person could jump. And I'm going to get my answer with feet. Notice inches to feet, inches to feet. So again, I'm just going to multiply both the numerator and the denominator by 78.72. So I get 5/3 times 78.72, and you should get 131.2 feet. That's if it could jump the same as a frog. So for 4, we have the actual length of the truck over here is 20 feet. And the scale model is 7.5 inches. Is this a unitless scale? And the answer, of course, is no. Because it's basically 7.5 inches to 20 feet. And the inches and feet do not cancel. Find the model scale of the actual length of a Ford Focus is 13.4 feet. So this is scale to actual. Just be careful that way. So I have 7.5 inches to 20 feet is the scale model, and I didn't do anything with it. So therefore, I want to find out what the scale model is if the length of the Ford Focus is 13.4 feet. I don't have to do any conversions here. Cross multiply and divide, put it on pause, and check your answer. And if you got 5.025, what's that? Is that feet or inches? Yes, excellent. Inches. That would be the length of the scale model from Ford Focus. That's 14.4 feet long. So find the model scale length. So I'm going to put down my actual scale. 7.5 inches to 20 feet. If the actual length, right? So the actual length is going to be 636 inches. But it's going to cause me a problem. See what the problem is? I'm not going to have inches to feet, inches to feet. So I got to convert this to feet. And I'm using dimensional analysis here, right? The inches are going to go in the bottom because I want them to cancel. So it's just 636 divided by 12, and I'm getting 53 feet. And that's the actual length. That goes in the bottom. Then I'm going to get an answer here for the length of the scale model length. So hopefully now you can cross multiply and divide and put it on pause. And I'm getting 19.875 inches. For the length of the scale model. So below is a map of a coastal chart that shows the distance between 2 points in Maine. Actually, I live right here, and that's where my voice is actually coming from right now. And this here is John's Island, so it's a trek out to right here, which is the Pembroke Point Lighthouse, which is the lighthouse on the 25-cent piece from Maine. So, okay, this is a coastal chart. It provides excellent detail for small harbors. And the scales are between 1 to 40,000 and 1 to 80,000. Hopefully you know now that they are unitless scales. Remember, if the scale is 1 to 40,000, that's the same as 1 inch to 40,000 inches, or 1 foot to 40,000 feet, or 1 yard to 40,000 yards, or 1 whatever to 40,000 miles, or centimeters, because it's unitless. All right, the scale of the coastal chart at left, that's 1 to 60,000, right here. And the distance from St. John's Island, which is right here, to Pembroke Point, which is right here, is 3 3/8 inches. You might need some of this detail here. So let's look at what they're asking us. They're going to ask us to find this distance here in miles. Okay, so just to go back, this is 3 3/8 inches. 3 3/8 inches, the scale. And our actual unitless scale is 1 to 60,000. So I've got 1 to 60,000. So if it's 3 3/8 inches, I could cross multiply and divide, or I could just multiply 1 by 3 3/8 and then multiply 60,000 by 3 3/8. And what would you get? And I'm getting 202,500. 202,500 what? Inches to inches. So if I want to change that to miles, I better come up here and look at this information here. So now I'm in the dimensional analysis, right? So I've got 202,500 inches times 1 foot to 12 inches, so that the inches cancel. And I now have feet, but I want miles, so I want to get rid of the feet and insert miles. And there's 5,280 feet in 1 mile. So I'm going to multiply 202,500 and then divide it by 12 times 5,280 and see what you can get. And I got 3.196 miles. So the distance from here to here is about 3.2 miles. So now let's do the same problem in nautical miles. Nautical miles are, it's a little bit different than miles. It's used in sea navigation. You ever hear somebody's going 17 knots or boat goes 16 knots? It's what they use in ocean-going navigation. So now we're going to find the distance in nautical miles. We have the same scale, 1 to 60,000, unitless. We know the distance in inches. I'm converting that to a decimal. So we're going to get the distance in inches. Cross multiply and divide, we're going to get the same answers we got above, which is 202,500. I would put this on pause now and see if you can make this, and that's going to be inches. See if you can make the translation into nautical miles. So hopefully you set it up this way, and you can see what cancels here. Let me do it in red. The inches are canceling. The feet are canceling. I'm going to be left with nautical miles. So if you do the math, you should 2.78 nautical miles. What's the difference between nautical miles and miles? Well, let's look at that. So a little history on why they call these knots is because they would have a coil of rope in the front of the boat attached to a piece of wood, which represented right here, and then tied every so often to a knot, and then another knot, and then another knot. So they would throw this off the boat. The boat, of course, would be moving forward, and they would time it to the wood got to the stern of the boat back here. And then they would just simply count how many knots it took and how long it took. That's how they determine speed. So here's our last problem. It's a little tricky. So miles per hour, kind of know what that is, right? And knots is nautical miles per hour. So knot is a speed. Nautical miles is a distance. We knew the distance in miles up here, and we calculated that to be in our last problem 3.196 miles. And we know the distance in nautical miles, which we calculated to be 2.78 nautical miles. And now we also know the time. 30 minutes. So we want to find, that's minutes, we want to find the speed, how fast it was traveling. Well, recall from, right, our famous equation, distance equals rate times time. So we know the distance and we know the time, we want to find the rate. So we're going to divide both sides by t, right? So the rate, or the speed at which something's going, is the distance divided by the time. So let's do miles per hour. So the rate in which we're going is the distance, which is 3.196 miles, over, you think about it. Am I going to put 30 minutes here? Or am I going to put something else? Well, I'm going to put 0.5 hours because I want it in miles per hour. So we'll put that on our calculator. And I'm getting 6.392 miles per 1 hour. So now let's at nautical miles. Same formula. The rate is equal to, in this case, 2.78 nautical miles divided by, again, 0.5. If I divided it by 30, I would get an answer. And what it would be nautical miles per minute. And that's not what we want. We want knots, which is nautical miles per hour. So we'll put that in our calculator. And I get 5.56. And that would be nautical miles per 1 hour.